Hi everyone, hi Quentin, and let's talk about the SAMD and what you can do with it during the Fab Academy.
Yeah.
So we'll try with a little bit of theory so that you know what we're talking about. Why you can use the SAMD in the Fab Academy. First thing is that they are much more powerful than what you use usually. So the AVR family, what you use on Arduino Uno, what you've used during previous Fab Academy, basically, or the new ATtiny family, RAVR. And now we'll talk about the SAMD that are much more powerful microprocessor. The first thing is that they are able to run at higher speed than the AVR usually. You can change the clock, but usually they are capable of going higher, about 48 megahertz. They have a more complex instruction set, which is called IRM. So they can execute more complex instruction actually. And they also support USB natively. If I have only one thing to push is that USB in hardware, which is very efficient, and that will prevent you from having to have a translator like USB to serial that you can find on Arduino. If you have a look on classical Arduino, that's Arduino Uno, and you can see on backward then there is a small translator that will translate USB to serial.
Yeah.
That you don't need in SAMD because you have USB natively. They usually have more flash or RAM, depends on the model, of course, but the family goes higher than the ATtiny family, and they usually have more and more advanced peripherals. On the ATtiny classical, you have one UART. You will find at least two or more. You can have SPI, I2C, ADC, DAC, and so on. They are globally more advanced peripherals. Just for a comparison, Arduino Uno, that you certainly know, has 8 mega 328, sorry. And the Arduino Zero, bad name because Zero is actually a higher version, has a 80 SAMD 21. Warning, really important, is that globally the SAMD work at maximum 3.3 volts. If you put 5 volts on one pin of the SAMD without controlling the current, you will more than probably kill it. Okay, just for small comparison, Tiny 44 and 85 are the old we used in the previous Fab Academy. They are programmed both by ISP, so we used the old ISP programmer here. Maybe you can show it. So that was the previous version we did during the Fab Academy. Then we have the Tiny 412, which is one of the new that are called Mega Tiny.
Mega Tiny,
yeah, they are programmed by UPDI that Adrian already presented. You have also the 1614, which is basically the same but with more pin and more memory. You certainly know the Mega 328, which is the Arduino Uno. And now we'll talk about the SAMD. You can see that they have globally more pins, more memory, and more RAM, and they go at higher speed. And they are programmed through SWD, which is basically JTAG. You can also compare the price, because you can see that for the same price, basically, you have much higher capacity. So that's one of the reasons why they are also interesting. So what's the difference between 32 bits and 8 bits processor? Of course, they will manage more bits, but what does it mean? Basically, they will be able to handle higher numbers. Higher numbers doesn't mean that smaller processor can't count on 32 bits. They can, but they will need a lot of instruction to execute the calculus. So you can't chain maximum, for example, 8 pin at one time, no more. in one cycle instruction. With 32 bits, you can do it directly. So globally, the idea with 32 bits is that they can execute more complex on higher registers. And so in one cycle, you will do more than one cycle on classical AVR 8 bits. So I already talked a little bit about USB. The USB is supported natively on SAMD, and that means that you can do two things basically. There is two classes which are really common and widely used on Linux, Mac, and Windows. It's USB CDC. It's a generic class that makes basically UART. So it's exactly the same as the small translator you have on the Arduino here. So the FTDI chip is not an FTDI, and it does the same. So you can do this. You can do serial through USB, and also you can do USB HID. And just for fun, we'll show you what we've used here to switch between our screens. I don't know. Quentin, can you show?
Yeah, it's a bit tricky, but so this is
basically it's a keyboard, and there is an ACMD inside. So if you push the first button, maybe. No, yeah, that one. Okay, and then you see us. It's a keyboard that is emulated through USB, and that's USB HID for human interface class.
Okay, so what can you do with an ACMD? There are a lot of great potential applications, but I just wanted to show you a few. This one is an Arduino-like board, which I will show in greater detail later. But basically, it has this USB port, you connect to your PC, and then you have those GPIO pins, which you can control in a way you are used to. This one, it's sort of do-it-yourself FTDI. It has this USB, and here the usual FTDI pinout. And there's a great new feature which we will show you later, because we noticed a lot of people would manually set the baud rate. But now we made a special Arduino sketch to dynamically detect baud rate change requests by the PC. So now it will actually behave like an FTDI. It supports all features, even bit parity change dynamically. So yeah, that's a great application. We'll show it a bit later. This one, it's more for fun. You see a photo transistor here. No, it's a photodiode actually. Yeah, and it has again many USB ports. So the idea is that it would feel something go here and simulate a keyboard press whenever it detects something. Then you have those more serious applications here. For instance, you have an SAMD that is next to an ATtiny, so it can program it. This is something we want to show later. I think we will. All right. So yeah, now we want to show you more practical things. So let's review a few boards that we have selected. This one, of course, I'm very biased, but I like it.
That's a good one.
It's the board I showed you, which behaves a bit like an Arduino. So the idea is that there's no hassle. You just connect it. It's compatible with Arduino IDE, and you directly see the pins because they are labeled on the copper. This is really something I wanted. It has a built-in LED. And the serial port, you can see it on the top left here. I added a protection on the RX because, of course, it's designed to use 3.3 volts, but let's say you really want to connect it to a 5 volt serial. In that case, it will be protected. But it's still not ideal. You should definitely use it in a 3.3 volt environment unless you can actually translate the voltage levels with a logic adapter. Right? Yeah, one last thing I wanted to mention about this. By default, I always use mini USB ports, but they are quite tricky to solder. So if you don't want that, you can you have another version with a copper USB port directly on the plate. So next we have the SAMD. We don't have one to show you right now, but it's another great board with a lot of documentation by Adrian. And the great thing in this case, yeah, you can open the dock maybe. Yeah. So you see that the pins are labeled also somehow. And what we like about this one is that he made an entire ecosystem of devices that you can plug in. So maybe you can go back to the slide. You see here there's, for instance, a device to control a motor. You just plug it in, the pins are directly aligned, so it's pretty easy to play with, I would say. It's designed with Eagle, so you have to take that into account. So next I will let Nicolas talk about his new project.
I just for fun, I tried Nils code with the Quantin GPU porting. So I created what I call SAMD. It's just an excuse to have a SAMD 11D, which means that's basically the same as 11C, but with more pins. So if you need more pins, or you need a true serial that you have access to, or to SPR or so on, you might go to the 20-pin version. So just for spot, I create conditional code. So it means that you can just change one thing into the code. You'll see that I will just change the value. You see here I don't want the con 10 but con 4, and you can see that the connector just changed here. I can change in other side because I don't like the small 0.5 connectors. You can go back to the 10 pins usual JTAG connector, and I also can change the regulator and so on. So you just have to change one or two variable, and the whole board will adapt. So I've let the old regulator. I will rechange the connector. You see that the old board will adapt like automatically. So that was basically.
One thing I wanted to mention about this, you see that it updates really fast, which is something you might be surprised about if you use the PCB Python code in the past. That's because we have the new GPU rendering, and that's something I will show in a separate tutorial if you are interested.
Yep. Also, I created a small SAMD 21 board. Continue, you can show this. That's a very small board. As you can see, I hate the too small or the milled connector. So I also always put a classical USB connector that make them robust, because there are boards that I want to use to make my developments and to get more used to those SAMD.
Something you might want to mention, it's the pins to program it, because quite often you will find these tiny 10-pin JTAG connectors. I try to use them as much as possible because you have those programmers that come with that kind of tiny cables, but that's completely optional. You can do without. So in this case,
I'll do it like more manually, but that's written in the documentation. So why I did this one? Just because if you look at the capabilities of the SAMD 21, there is much more flash and much more RAM than the other SAMD we just presented. So that's the good reason for using them. The only thing is that they have a package which is a bit more trickier to solder. So I will recommend this board only for a bit more advanced user only. And I choose the E version because it has only 32 pins instead of much more. And if you have more pins, they are closer and even more difficult to solder. So I think it's a good trade-off between difficulty to solder and to make the board and the capabilities of the microprocessor. So how do you install EDBG now? EDBG is the program you will use to load your code inside the chip. So under Linux, it's kind of straightforward, a little bit less that under Windows content will answer, but so we made a small video with basically just cloning and copying the binary to the right folder. So it's kind of straightforward. You can have a look at the video if you take the slides. Quentin, about installing it on Windows.
Yeah, on Windows it's really the same, but what I show here is if you want it on the path, you will probably want to...
Maybe you can explain what means having it into the path.
Yeah, so basically it's just an executable file, right? You put it anywhere on your computer, and if you open a terminal, you could launch it. But what you want is to be able to launch it from anywhere, not necessarily from that folder. So for that, you would add it on the path environment variable. Here you see I'm just copy pasting the folder where I put edbg, and that's it. Now I can open a terminal, and it's exactly as you would do it on Linux afterwards.
Yeah, so that's basically the same as copying it into the right folder under Linux.
Exactly.
Basically, so making it available from everywhere. How do you flash a bootloader? Maybe you can explain that part.
Yeah. So we'll show it in practice later, but essentially what you want to do is have a programmer. This one, it's a commercial one, but guess what? You can also make one from an SAMD. We don't have one right here, but Neil has some.
I do.
Some designs for that.
I do have one here. That's my version.
Yeah. All right. So this one is a programmer made from an SAMD. It's completely equivalent to this one. So I have this 10-pin JTAG, but what you really need is just the 4 signal pins. Actually, you only need 3.
You actually need 3 if you connect them on the same USB hub or same computer, as the ground is already connected in between, but that's good practice to connect the ground anywhere. So you need the ground, the clock, the DIO, and the reset pin, and you have all you need.
So you connect it, we'll show it later, but you simply launch edbg.
Yeah, we've noted all the options available here and what those means, the eBPV.
Yeah.
The first thing you have to do is to choose the right bootloader from Mattertech that has written all the proper bootloader. So we've linked this one to the proper one for the SAMD 11C, but if you need another one, they have nearly everything you need in the SAMD family.
And once you flash it with that bootloader, it becomes completely compatible with Arduino, which means you can also reprogram it without without edbg, which is really great.
So it also means that you don't need the programmer anymore. You'll need the programmer just once to put the bootloader, and that's it. Yeah. You can disconnect everything, and you can use it like a classical Arduino.
That's it. So once you've done that, you probably want to use it. So I showed here how to install the Arduino core from Mattertech. You just copy paste the JSON right here in additional URLs. Maybe you don't see it. Let me maximize. So once I've put the JSON address, it will be available in the board manager. Takes a bit of time to load. I install the latest.
That's basically exactly the same I did as Adrian already showed for the MegaTiny family. Yeah, basically the same. You add the JSON to the preferences, and you just install the library through the board manager.
And that's it.
And that's it.
That's all you need to do. Now it's going to be listed in the board options. And you see here I choose a D11C14. And once I've done that, I have a bunch of options that are specific to that. We'll show them in more detail later, but some of these are really critical, especially the 4K bootloader, because this is what we just flashed on the thing. All right. I think that's it. Yeah, let me escape. Next, I think that's all we wanted to cover for the theory. Now we're gonna show you some practical stuff.
Yeah.
This one, last bit of theory, if you wish. If you want to use it as a serial adapter, as I mentioned earlier, there's this new code I prepared,
which is based on Neil's code, but
Yes.
that were kind of static, and Quentin made it dynamic, let's say.
Yeah, so now you will see that it can detect any baud rate and any mode you want when you change it through the computer, because CDC allows for that. That's really important. Okay?
That's it?
I think that's it. Hello again. Now we will have some practical session. Unfortunately, Nicolas couldn't join this time, so it's just gonna be me. And I have a little setup here. So we have the development board that I presented earlier, and we also need a programmer for this board. So in this case, it's a commercial one, but you can use any other as long as you have the JTAG pins. In this case, I'm using a 10-pin mini connector. So here's the list of topics that we'll cover. We will first see how to flash the bootloader onto the chip. And after that, we can use it as an Arduino board. So using the Arduino environment, I will show how to use the SAMD as a keyboard, as a serial adapter, and finally how to debug it with OpenOCD, which is a much more advanced topic, but it's also very exciting. I'm sorry for the sound quality, and I hope you enjoy these topics. Okay, hello again. Now it's time to do some practical stuff, I think. So I prepared right here one of my boards. This one is the Arduino-like board with all the pins labeled, and it has the mini USB connection here, and we will first flash the bootloader using the JTAG connector. Okay, so I'm gonna take my my programmer here. It's a commercial one, but as mentioned earlier, you can perfectly make your own using an SAMD. And I have to connect this 10-pin JTAG connector. So you have to get this right. It's very important because you could connect it two ways, as I didn't put any blocker here. So in this case, I know that the end where you have the little notch, it's going to be the power line. Let's look at it here. Yes, so you see that where you have the notch, it's the side where you have the ground and the VCC. On the other side, you have all the data connections. So in the case of my board, you can see that the ground is on this side and the data lines are on this side. So let's be consistent and it should be okay. So I'm gonna plug it in this way with the notch facing outwards. And okay, we are all set up. I can first, maybe I will power the board. And you see that we have the green LED, but nothing else. As this board is completely new, it has no firmware and no program to run. So now I also have the debugger plugged in, and let's see what happens here. I can ignore that, and if I take a terminal and I list it, I will see that the debugger is correctly detected. So that's nice. And now we can do all sorts of things like programming, flashing the bootloader. Okay, so I downloaded the binary file for the bootloader. It's the one we mentioned earlier. It's right here, and I can just first specify that it's an SAMD 11. I want to erase it in case there was still something else. And then I want to program it. I will also enable the verbose and verify. Okay. And then I have to give the location of the binary file. And it's done. So now you can see right here that the SAMD is immediately detected by Windows. If you go to your device manager or your control panel, you will see it as a new device. A lot of stuff here, but you can see that there's a new device here. And it's actually on SAMD. Okay, now it even has a name. So you see it's a serial port. As simple as that. Now if I go to the Arduino IDE, I will also see it. Right here, it even has a name. And we can start using it like an Arduino. Actually, at this stage, I don't need the debugger anymore, so I will just remove it. Okay. So now we have a nice board with the bootloader. Let's start with a very, very simple program which will simply blink the LED. On my board, I have an LED on pin 15. As you can see here, pin 15 also gets to an LED. So let's try that. I will first select the correct board type. As we shown earlier, it's very important that you install it first. Then you will see this package and you can select the D11C14 in this case. Okay, now for the options, I could enable the HID. That would actually let me pretend it's a keyboard or a mouse. Then I could do really interesting stuff, but let's not enable it for now. And also, if you want to use the serial port, you will most likely need to enable this option right here to UART. The reason is that one of them, unfortunately, it's not. It's already taken by other pins. I think some of these pins belong to the JTAG connector actually. So you could, in theory, you could get 2 serial ports from this, but I'm just gonna use one of them. And it's right here. You can see RX, TX. I enabled them. So this is the serial port on my board. The rest of the settings, yeah, the bootloader. It's very important that you say it's the 4K bootloader. Otherwise, you could have really strange things. It has to do with the address shift, I think. Because, you know, 4K is already taken by the bootloader, so you have to always take it into account. I think that's it for us. So we'll just select it and program it like you would program any Arduino, basically. You can see it's compiling. Now, for some reason, with that specific package, it's pretty slow for me. It takes up to 10 or 15 seconds to fully upload the program, you will see. Still compiling, okay. So it says 76% of the program storage space. I think that's also a bit abnormal because it's really such a simple program here. So I think they didn't optimize the library very well, maybe, but it doesn't matter because in the end it works. And now it's writing to the flash. Almost done. Okay. So you can see it's blinking. And yeah, that's basically it for this board.
So now I just wanted to show you some keyboard examples. So to use that, it's very important that you select here the HID setting in USB config, okay? So once you've done that, you can go ahead and include keyboard.h. You enable it, and after that you can do whatever you want. So in this case, I'm gonna print some text if I detect that a button is pressed. So let's connect the button. So I've prepared a pull down button here. I'm gonna connect it to the pin number 8, and that's really all I need. It's gonna pull it down to the ground when it's pressed. If you look at the code, you can see that I configured it as an input pull-up. So the SAMD, like almost any microcontroller, has pull-up inputs. It's a pull-up resistor that will put it to a high logic level when it's floating. And when it's not floating, then it's going to be pulled down by the button. And I'm going to be able to read a change and do some stuff. In this case, I'm going to blink the LED and print some things with the keyboard. So let's flash it. Now, of course, you have to be super careful when you use the keyboard library, because it could make your chip almost unusable. If you just print some random stuff all the time, it's going to be very annoying for your computer and for you. And something else you need to keep in mind is that those characters are actually scan codes. So you will have some nasty errors if your keyboard is not QWERTY. Those scan codes were designed for QWERTY. So yeah, that's the tricky part. But other than that, it should work pretty well. It's still flashing. And also it should appear as a keyboard because now it's using HID, so it's pretending to be a keyboard. Let's see if that's the case. Yeah, it's right here. It's labeled as a keyboard. So let's see if it works. Let me just put some blank space, and yeah, every time I press the button, you see a small blink on the LED, and it's just prints some text. Okay, so next I wanted to show you the SAMD serial code that I prepared. It's available on GitHub, and what it does is it turns your SAMD into a serial USB bridge. And you can automatically detect the baud rate, parity, or stop bit change, just like you would with an FTDI. So that's very convenient in practice, as you can expect. So this is the Arduino sketch that is included. And as usual, you have to make sure that you enable CDC, because this is how the serial port works on the USB side. And here I have to enable 2 UART. So what this option does is that it enables RX and TX on pins 4 and 5. Otherwise, you simply have one serial port, which, as I mentioned earlier, it's not available. So let's go ahead and just flash it. Yeah. So you see that there's a default baud rate, but it doesn't really matter because the computer will immediately request the baud rate whenever it opens the port. One other thing here is that I connected RX and TX together as a test, so that whenever I write something, it's gonna ping back, because it's gonna be read by RX, of course. So it's almost done flashing. Yes, and now I can simply open the serial monitor as you would with any Arduino. And it doesn't matter really which baud rate I selected, because it's automatically detects the changes. So let's say I have 9600, and it just works as expected You have to trust me for this. I could show you with an oscilloscope, but yeah, this baud rate change is really effective. Now, one great application for this is UPDI programming, for instance. So I have here an ATtiny 1614 that I want to program, let's say. So of course I have to power it first. So let's take the ground and the 3.3 volts. And then you can see there's already some program there. And this pin, it's the UPDI programming pin. So what I'm gonna do is I'm gonna put it right here on RX. And then you have a resistor that goes to TX. And that's really important for UPDI. You see here that you have the UPDI pin on the target, and on the other side you have TX and RX together with the 4K resistor. I use 10K in this case, but it's gonna work just fine. So I need to have a program, of course, for the ATtiny. Let's take this one. So it's just gonna blink the LED. You can see that this time I'm using the Mega Tiny core because it's an ATtiny. I'm not changing any settings, but I am gonna select my SAMD serial port because that's gonna be my programmer. And now the great update that we have with ATtiny, the Mega Tiny core, is that you can directly program it through Arduino if you use this programmer. So serial port plus the resistor. If you do that, then let's see if it works first try. Then I'm gonna be very happy. So it's still compiling. Yeah, this is it. It worked. So what you saw right here is an embedded version of PyUPDI that we have included in the new Mega Tiny core, and it's using the SAMD. In this case, it's using it as a USB serial bridge to communicate with the UPDI pin of the target. So that works fine. Okay, so finally I wanted to show you how to debug an SAMD using OpenOCD. Now, I'm no expert for this, so it's going to be very brief, but it should give you a small glimpse on the amazing possibilities that this could offer. So let's say I have my debugger, and I'm going to connect it as we did earlier to flash the bootloader, but this time it's going to be for real-time debugging. Okay, so now it's gonna appear. I have to install OpenOCD. In my case, I'm on Windows, so I simply picked a pre-built binary. And what you will see is you have a bin folder, and in the share folder you have a bunch of scripts. Now in my case, those are all configuration files, and I was looking for one that was compatible with my SAMD, so I picked the SAMD 11 config file. Okay, so I copy-paste it to a folder here, and I renamed it openocd.config. Now let's see what's inside. Yeah. It's really short, but you can see that it actually includes some more complex configuration from another file. That's okay. So now let's simply launch it. OpenOCD. It has to be on your path as usual. and it just works. And you can see the debugger going all crazy here because it's communicating all the time. And something really interesting here, it says that it's listening on port 3333 for GDB connections. GDB is the open source way to debug. If you use Linux, you probably know it better than I. And what it means is that now OpenOCD is ready to take requests from GDB. Now you might be wondering which GDB, because we didn't install any. Well, actually, you already have it, because Arduino comes with a bunch of really important stuff. For instance, you have the compiler here. That's how it can compile your code. And one of these binaries is GDB. So it's right here. So let's put some new code on the SAMD. I have a very simple sketch here, and instead of uploading it, I will just verify it, which will compile it. And I will also enable the verbose output. So this way, when I compile it, I will see all the folders. It's pretty important for me because I'm looking for the compilation files. And what you see here is the ELF. Now, it's not the binary that goes on the chip, but it's an intermediary file for that. And this is what GDB is looking for. So I have to give it to GDB. Let me just copy paste it. And you can see that I prepared some pretty complex commands that says to connect to the port 3333 on localhost, because that's where OpenOCD is ready for me. Now let's just take a different terminal. Let's simply drag and drop GDB because it's not on my path yet. And now we have the rest of the command. And that's it. It started. It's not complaining. And I can do load. This actually sends the binary to the chip, but it doesn't start it yet because for some reason you have to do monitor reset, then monitor hard. I'm not exactly sure why, but yeah, there we go. So now if I do continue, you can see that the chip is running the program, which was simply a blinking program. And whenever I break it using Control-C, for instance, it's paused because I stopped the execution of the program. And we can do some really fun stuff. So, well, as I said, I'm no expert, but I at least know that I can look at the backtrace. It gives me the stack. So now it says I'm at line 11 in my sketch, okay? Which probably corresponds to one of these delays, one of the two. So I'm gonna put a breakpoint there, which you can do with B. And now we have a breakpoint. So now, if I continue, I'll just see, it's gonna run and it's gonna stop at that breakpoint again. And we should see the LED blink just once. Yeah, so now every time I continue, it's gonna blink. So it works. One other thing we can do is just take a variable and monitor the value. I think that's quite amazing. So here I have variable A. It's simply a counter. I can do, I think, display A. That should work. Yeah. So now I see the value for A. And every time I continue, the breakpoint is reached and I see the value for A. I think that's quite amazing. Yeah, so that's about as much as I'm comfortable with, because I really don't know GDB, but I think there are some experts out there that can really use this to debug advanced programs. Okay, thank you very much.